In the deepest black of the ocean, a nearly invisible shrimp bursts with blue-green light inside its own transparent head, a hidden firework exploding where no sunlight ever reaches. This spectacle is not just camouflage. It is survival, confusion, and communication fused into one. How can a creature made almost entirely of glass conceal such a violent flash inside itself? And what drives this evolutionary paradox? The answer begins with the anatomy of a shrimp that vanishes until it decides not to. In the open water far below the reach of sunlight, a transparent shrimp hovers nearly undetectable. Its entire body is built for disappearance. The tissue is so clear that even powerful underwater lights struggle to pick out its outline. Muscles, nerves, and organs are packed inside a shell that scatters almost no light, leaving only a faint shimmer where the animal drifts. In some species, the heart and digestive tract are visible as pale threads running through the torso, but the rest of the shrimp seems to dissolve into the background. Predators scanning for movement find nothing but empty water. The shrimp's glass-like exoskeleton bends and transmits light rather than reflecting it, erasing shadows and making the animal nearly invisible from any angle. Even at close range, the shrimp's limbs and antennae blur into the darkness, their edges lost in the water column. This extreme transparency is more than a clever trick. It is a survival strategy in an environment where any shadow could give away a meal. The open ocean is a hunting ground for fast, sharp-eyed predators. For a shrimp, vanishing is the first and best line of defense. Only the most vital organs, clustered just behind the armored head shield, break the illusion of total invisibility. Everything else is designed to escape the eye, setting the stage for an even stranger adaptation, hiding a burst of light inside a body made of glass. Inside the shrimp's armored head shield, life is packed tight. The space just behind the shell holds a dense cluster of vital systems: the heart, the main arteries, the foregut, and the upper reaches of the nerve cord. In some species, the gills and the beginnings of the digestive tract are wedged in as well, all layered within millimeters of the outer carapace. X-ray scans and 3D anatomical models reveal a crowded control center, with each organ pressed against the next, separated only by thin membranes. Blood vessels thread through this region, branching from the heart and looping around the brain, which sits at the very front, shielded by the hardest part of the exoskeleton. The shrimp's main sensory processing happens here too, with nerves fanning out to the eyes, antennae, and mouth parts. The sensory wiring and the motor wiring are all routed through this small space. This compact arrangement means that nearly everything essential for survival runs through the head: circulation, digestion, sensation, and movement. Yet because the shell is so thin and clear, these organs are exposed to the outside world in a way that almost never happens on land. There is no thick skull or opaque armor to hide them. Instead, the shrimp's head becomes a stage where delicate tissues and hidden machinery operate in plain view. This anatomical setup, forced by the need to stay small and light in the water column, creates an unusual opportunity. It allows for the possibility of building a light source right in the middle of the most protected, most crowded part of the body. In this transparent chamber, a shrimp can hide its most spectacular secret: a burst of light ready to ignite at any moment. Hidden just beneath the shrimp's clear head shield lies a set of organs unlike anything found on land. These are the organs of Pesta, clusters of bioluminescent tissue pressed tightly among the heart, arteries, and the first loops of the digestive tract. In three-dimensional scans, they appear as slender branching tubules, running along the underside of the carapace and flaring out toward the edges, like tiny lanterns built into the animal's frame. Each organ is organized into distinct regions: a reflective cap loaded with carotenoid pigments and lipids, a central core dense with light-producing cells, and a distal filter lined with microvilli that shapes the final beam. The reflective cap bounces light downward, while the core is packed with paracrystalline platelets, ordered stacks of proteins and membranes where the chemical reaction takes place. Here, coenterozyme and luciferase meet in a burst of energy, producing a flash of blue-green light that fills the shrimp's head from within. This entire system is only millimeters thick, yet it is threaded with a labyrinth of blood vessels and nerves, all crammed just beneath the glassy surface. When the organs ignite, the effect is immediate. The shrimp's head glows from the inside, as if a firework has gone off behind frosted glass. The rest of the body remains nearly invisible, so the light seems to hang in the water, unanchored to any obvious source. Slow-motion footage from remotely operated vehicles captures these flashes in real time. One moment the shrimp is nothing but a faint outline, the next its head blooms with color, then fades back to darkness. The organs of Pesta are not just biological curiosities, they are hidden lamps, perfectly engineered to unleash a burst of light in the most vulnerable, most exposed part of the shrimp's anatomy. A transparent shrimp's light show is more than a simple flash. Deep below the surface, survival depends on precise control. When a predator lurks below, the shrimp can ignite its internal photophores, dialing the intensity up or down to match the faint sunlight filtering from above. This trick, called counter-illumination, erases the shrimp's shadow and turns it into a floating ghost, visible only if it chooses to reveal itself. The light is not random. Specialized reflectors inside the organs direct each beam downward, blending with the ocean's natural glow. In the right moment, the shrimp can even shift the brightness in real time, fine-tuning its camouflage as the light environment changes. Not all shrimp rely on hidden fireworks. Acanthophira purpurea, for example, ejects a glowing blue cloud from its digestive tract, a smokescreen that floats and glows, leaving predators chasing after light with no shrimp inside. Lanternfish and hatchetfish use rows of belly photophores to wipe out their silhouettes, a convergent solution to the same problem. Ostracods fire off rhythmic pulses to attract mates, turning bioluminescence into a secret code. Firefly squid create coordinated patterns along their bodies, luring prey or signaling to others in the dark. What sets the transparent shrimp apart is the versatility of its internal system. Its organs of Pesta are built to respond instantly, producing a hidden burst or a steady glow depending on the threat. The chemistry is self-contained. No symbiotic bacteria are needed. Every flash is a product of the shrimp's own enzymes and careful regulation. In this underwater arms race, the shrimp's toolkit is both shield and spotlight, adapting to shifting dangers and opportunities in the deep. Recent discoveries reveal an unexpected twist inside the shrimp's hidden light organs. These photophores, once thought to be simple biological lanterns, contain the same light-sensitive proteins found in eyes called opsins. Genetic analysis shows that the organs of Pesta express opsin genes, giving them the machinery to not only emit light, but also detect it. When scientists exposed these organs to bursts of blue-green light, the tissue responded with microscopic changes, shifting internal pigments, as if reacting to a sudden flash. This suggests the shrimp's light organs may act as both lamp and sensor, creating a feedback loop where the animal can sense its own glow and adjust it in real time. Instead of relying on vision alone, the shrimp is equipped with a network of light-sensing cells embedded right inside its skin, allowing it to fine-tune its underwater fireworks with astonishing precision. The story of shrimp bioluminescence is still being written. In 2021, a global survey of deep-sea expeditions and research cruise logs pushed the count of glowing shrimp species to at least 157, a jump of more than 60% from previous estimates. This leap did not come from one single discovery. It came from years of archived footage, re-examinations of specimens, and the tireless work of marine biologists piecing together clues from every ocean basin. The true scale is likely even greater. For every species captured on camera or preserved in a jar, dozens more may be flashing their hidden fireworks in total darkness, unrecorded and unnamed. Each expedition uncovers new variations, different shapes of photophores, new patterns of light, and unfamiliar behaviors. This reminds the scientific community that the deep sea still holds far more glowing secrets than answers. Every year, new expeditions reveal more shrimp lighting up the dark ocean, proof that nature still holds secrets in plain sight. As deep-sea technology advances, the search for hidden life intensifies. The next burst of light in the abyss could change how we see our own planet.